All right, in this video, I want to talk about section 2.7 and 2.9. We'll come back to 2.8, but I think 2.9 is closely related to 2.7, and that's why I want to deal with them together. All right. 2.7 sets up your analysis model for constant acceleration. So what does that look like? Well, we described the average acceleration before. And if it's constant, then it's just equal to the average the whole time, right? Now we're going to use, of course, that our t initial is 0 and our t final is just t. And that gives us that ax then can be written as vx final minus vx initial over t. And we can solve that with a little bit of algebra. If we just multiply by t, and if we add the initial value to each side, we end up with the final value is equal to the initial value plus ax times t. So this is, excuse me, this is one of our standard kinematics equations. I generally refer to this as the velocity equation because it's your velocity as a function of time, right? If you're given your initial velocity and the acceleration, then you can describe the velocity at any time. All right, where do we want to go next from there? Well, it works out that, well, let's look at this. If we have a v versus t, and we have a constant acceleration, thus a constant slope on v, then v average is just the average value of that. And I wrote age again instead of average. V average is the average value of that. And you can look at this graphically and see that it's just the middle value between V naught and V final, right? If I were to chop off this and just flop it over here, then I would have the same volume, right? Or not volume, the same area. And that area would be V average the whole time. Right, so how do we write that mathematically? If we want to average just the initial and final value, that would be the final value plus the initial value divided by 2 would give us the average V. Oops. All right. And how do we want to make use of that? We can recall our distance equals average velocity times time equation and use this for our average velocity, right? So if we say delta x is equal to v average times t, and we now plug this in, then we get delta x is v final plus v naught over 2 times t. You'll sometimes see it written as 1/2 v final plus V naught times t. And this one I call the, surprise, surprise, average speed equation or average velocity equation. EQN is common abbreviation for equation. Write it a lot. All right, so we want to take our next step from there. If we look at our graph here again, how can I describe V final looking at this? Well, let's sketch some. All right, here's V naught. And the velocity changes based on the acceleration. Well, we've already got our equation up here, right? But you can see how it arises graphically too. This is my V naught, or I've written it as sub I here instead of sub O. And the change is A times T. So that gives us our V final equal to V initial plus AT. And we can now plug that in to the last equation that we got, the average equation. And what happens when we plug that in? So I've got delta x is equal to 1/2 V final plus V initial times T. And I'm now going to take this and plug it in for V final. So now I've got delta x is 1/2. What did I plug in for V final? I plugged in V initial plus AT. Right. This term is replaced by this term, and then times t. So let's distribute everything and simplify. We've got 1/2 times 2V naught plus AT times t. Distribute the 1/2, and we'll have V naught plus 1/2 AT times t. Distribute the t, we get V naught times t plus 1/2 AT squared. So delta x equals V naught times t plus 1/2 AT squared. More often, I tend to write this as your x as a function of time is your initial x plus V naught times t plus 1/2 AT squared. Again, this is one of our major kinematics equations. And this is the one I refer to as the position equation, because it describes your position as a function of time. If we want to do a little algebra, we can do some elimination. Eliminate t. So how do we want to eliminate t? I think I'm going to take the position and the velocity equation and eliminate t. I think that's the easiest way to do it. So if we take v is v naught plus at, and we take x equal to x naught plus v naught t plus 1/2 AT squared, I'm going to, what's going to be easier? Delta x b. I guess you just have to solve this one for t. It's going to be too complicated the other way, right? So let's take equation 1 here and solve for t. So if we take equation 1 and we solve for t, we'll have v minus v naught over a is equal to t. Uh-oh. Click. There we go. So now I can take that and sub it into equation 2. that yields. Now we're subbing into equation 2. So x, I'm just going to write x minus x naught as delta x. So I'm going to bring the x naught over. V naught, and again, we're subbing in. So subbing in for this t and this t, we're going to sub in this representation. So v minus v naught over a. And 1/2 a, oops, I wrote the t again even after subbing in. V minus v naught over a squared. Okay, so we've got delta x equal to v naught v minus v naught squared over a plus 1/2 a times v squared minus 2v v naught plus v naught squared over a squared. Right there, I've just squared the top and the bottom using the binomial square on the top. Right, square the first plus 2 times the product plus the square of the lengths. So if we simplify again, we've got delta x is equal to v naught v over a minus v naught squared over a plus 1/2. One of the a's is going to cancel. So we're going to have 1/2 v squared over a plus, oops, minus, the 2 will cancel with the 1/2, v naught over a plus v naught squared over a with a 1/2. Plus 1/2. All right, let's multiply everything by a to clean it up. And we'll multiply by 2 to clean it up too. Maybe I should have done that before distributing the 1/2. So 2a delta x. So we're multiplying everything times, let me write it out here to the side. We're going to do times 2a. So when we multiply everything by 2a, we get 2 v naught v minus 2 v naught squared plus v squared minus 2v v naught plus v naught squared. All right, what do we notice here? We notice that this term is going to cancel with this term. And I've got a math error somewhere. What am I messing up? I lost a term somewhere, something. No, it's right. I was just reading it funny, sorry. And these two terms group too. Oh, wrong color. I swear I clicked on the red. There we go. All right, so we're left with 2a delta x. When we group these two terms, we end up with a minus v naught squared, and this leaves us with a v squared. So we can now write this as v squared is equal to v naught squared minus, or yeah, plus, not minus, 2a delta x. And this we usually just call the v squared equation. Not very imaginative. But this one doesn't have a nice physical meaning like the others that's easy to access, right? This one's just derived from the algebra here. All right, and that is our analysis model for constant acceleration, and that's all for kinematics equations. So section 2.9 has you derive these from calculus. So we can say that AX is dVx dt. And then we can look at the definite integral associated with both sides here. So we can take dv equal to a dt, and I'm going to just drop the x because we're talking about one dimension here. So dv is equal to a dt, and that gives us, now we're going to integrate both sides, when we'll get v final minus v initial equal to the integral from 0 to t of a dt, which then gives us a times t, right? Because a is just a constant, the integral from 0 to t is just t. All right, and that looks familiar, right? That gives us our v final equals v initial plus at equation. All right, so we've now derived it from calculus. But we also know that Vx is dx dt, and we can do the same thing. So now we can say take this to dx equal to Vx dt, integrate both sides, x final minus x initial is equal to the integral from 0 to t Vx dt. That's going to give us final minus initial equal to have I made this too simplified? I think it's okay. I guess I did leave out one step in my notes here. Vx initial t plus 1/2 a t squared, which recovers our position equation, right? And even though we didn't get it from our analysis model that way, we could eliminate A to get our average velocity equation from these two equations. And of course, we could eliminate T the same way to get our V squared equation.